Okay, hello everybody and good evening. Although this is a physics stream, I'm going to be doing a little bit of biology just to begin with because I know a lot of you, probably everybody doing physics, will also have a biology exam tomorrow. So before we go into like the physics bit, which we're going to be getting onto later in the chat, so I'm just going to bring up my thing here. Evil, hello. Yeah, basically later on we're going to be doing some stuff with the next kind of Lego minifigure. We're going to unbox that, see what we have tonight. That's probably going to be about 8 o'clock. But before that, I just want to show you something that I think could be really, really useful. So this is an app not created by me, created by another teacher. And the app is called BioQuiz. Okay, there's a physics quiz, there's a chemistry quiz, but for you, obviously, you need this for tomorrow. It's an app it's a free download from the App Store. This is just on my iPhone here. I'll just zoom in a bit. It's not the greatest quality, but basically what you can do is there's notes to like other bits and pieces. If you click on launch, it brings up the different topics. So for example, we could look at maybe cell biology. We could look at the cell structure, and then it's just lots and lots of multiple choice questions. So when setting up a microscope to observe a sample on the slide, what magnification should you use first? Should you use any, the lowest, the highest, or midway? I'm going to say, I'm not very good at biology, but I'm going to say the lowest. Excellent. Okay, the next one, name cell structure B. So B is this bit around here. I'd say that that's not the cell wall, that's probably the cell membrane because it's the inner side. And again, another correct answer. So if you are doing Biology Paper 1 tomorrow, which all of you will be, head over to the App Store, download BioQuiz, and you can just use this just to kind of revisit the last few bits tonight before your exam in the morning tomorrow. There's also a chem quiz, I haven't actually used that, and there's the physics quiz I used in some of my live streams last year, but I think this one here is really good. So BioQuiz, have a look at that on the App Store. It's free to download. I think you can pay a little bit for extra questions, but basically that one at the moment is just for GCSE. So GCSE biology, GCSE chemistry, and GCSE physics. Okay, however, I suspect a lot of you might not be watching the stream tonight. You might be going to look at some of the resources other people have put out there. People like Primrose Kitten, I'd highly recommend a lot of her videos for last minute bits of revision. But there's basically loads of stuff out there that you can have a look at to really help you. But this live stream here, you might well be watching after the event. But I'm just going to go through it anyway. You can obviously catch up by going to my websites, either GCSE or A-Level Physics Online, and going to the live page to see everything. Okay, the first one is we've got a physics question here, looking at 2 points in a circuit labelled A and B, and then we have resistors connected between them in different ways. Two arrangements are in series, like we have here, and also in parallel. And then it says to predict the behaviour of electric circuits, it's often useful to calculate the equivalent resistance of an arrangement of resistors connecting the 2 points in a circuit. Okay, lots of information there. Basically, what do we mean by the equivalent resistance of an arrangement of resistors connected between points A and B? Basically, the equivalent resistance, I'm going to write in blue tonight. This is the resistance of a single resistor that would have the same effect as that combination of two resistors. Okay, so really what we're talking about here is basically the total resistance of these things here. Now for a series circuit, we're just going to add the resistances together. For GCSE, for AQA, you don't actually have to calculate it, but you need to know that if you have resistors in parallel, their combined resistance or their equivalent resistance is actually lower. Have I taught OCR before? I haven't taught it at GCSE, but I do have videos that support all of OCR physics at GCSE Physics Online, and I do have videos to support A-level OCR physics as well. Why does doing work on a gas cause internal energy to increase? So if you do work on it, there's going to be a transfer of energy to that video motioner. This for GCSE level. Basically, if you do work on something, you're applying a force over a distance, maybe you're compressing it. And as you do that, what we're doing is we're transferring energy to the gas. And effectively, if you had maybe two surfaces, you do some work and you bring them together, that means the particles are going to be, maybe colliding with each surface more often, so there might be a higher pressure. Or it might be as you're doing that, as this thing is moving, it's going to transfer some energy to those particles which are oscillating. That's probably not the best explanation. I do have, of course, a full video explanation on my website. Okay. Each resistor in figure 8 up here has a resistance of 47 ohms, and the cell has a potential difference of 1.2 volts. So what I'm going to do is I'm going to label my diagram. So that's 1.2 volts and that's 1.2 volts. Here we have a 47 ohm resistor, and that one's 47. And of course that's 47 and that's 47 as well. We're going to calculate the current in the series circuit above. Now there's quite a few different ways to do that. So what we could say is that the total resistance of those two resistors in series is equal to R1 plus R2. So that's going to be equal to 47 added to 47, which is equal to 94 ohms. Okay. We can then use the equation that says V equals I times R, probably one of the most important equations in kind of physics when you're looking at electrical circuits, and we can rearrange this to say that I is equal to V divided by R. Now the potential difference is 1.2 volts, and the total resistance of those two resistors that we've just worked out up here is equal to 94 ohms, and therefore you can say that's just equal to 1.2 divided by 94, which equals 0.01277. So the current would be 0.013 and the units would be amps. Okay, hopefully that's all making sense. So that's one way of doing it. Okay, we basically know the potential difference across these two things here, and if we know the potential difference across them, we know their total combined resistance, we can work out the current through that. Okay, so that first question isn't actually too bad. It's just looking at the arrangement of these components in that circuit. The next question then says, explain why the equivalent resistance of two resistors in parallel is less than the resistance of either resistor individually. Okay, so what we have now is this part of the circuit here. Okay, why is it that these two things, when they're in parallel, why is the overall resistance lower? And I suppose what we've got to think about is, I can explain how resistance in parallel works. And I think that there's often analogies that work really well for this. One of them is to think about maybe, and there's there's quite a few that you can use if it's maybe water flowing down pipes. So if you imagine you had a pipe like this, and you wanted some water to maybe flow from maybe a tank up here, and you wanted that water to flow down and out the bottom. If you've got quite a thin tube there, it's going to restrict the amount of water that can come out per second. But if instead, to that same thing, you had two tubes that were connected up to the water, so maybe we've got some water in this kind of thing up here, there's now two different ways that that water can flow through. So in the same amount of time, there's going to be twice as much water flowing through these. Now, even though each tube is still the same, we now have twice as many paths for the water to move through, and therefore the overall resistance of this is going to be less. And if you had more pipes for the water to flow through, more water would be able to flow per second. And it's a bit like that with current. Okay, but instead now, imagine you had one resistor, all the electricity is going to have to move through this. But if instead you had two resistors which were side by side, then actually some of the electricity is going to go this way and some of the electricity is going to go that way. So we can have current going in more different routes, and that means the overall resistance is going to decrease. So I suppose then we need to just kind of sort of state kind of what happens. You could basically say that, or do you reckon that's enough? I reckon that's okay. Okay, so basically the equivalent resistance is lower because there are more paths for the electricity to flow down. And actually what I did, so because there are two paths for the current to flow, the resistance is lower. You can also do some calculations, but basically what you could say is that you could say that the PD, or the potential difference between A and B over here, so the potential difference across each of these things is going to be 1.2 volts, because we have the same potential difference around any loop in that circuit. Now that means over this resistor we've got 1.2 volts over 47 ohms, but here that 1.2 volts was going to be shared, so we'd have 0.6 volts over here and 0.6 volts over there. Now we know that I is equal to V over R, so you're going to have a much bigger potential difference over the same resistance. You're going to have a high current in this, you're going to have a high current in this, and also the current is going to be doubled. So whatever the current is in here, you must have twice that current that's actually coming into that junction, which it then splits away from. Okay, so basically each resistor will have a greater current flowing through it than we had over here, and also there's going to be a bigger current here, and that's because we can have a bigger current because we have a lower overall combined resistance. Okay, if you do want to see the full answer, what you can do, I've got a kind of written answer over here that would be ideal for you to kind of put down in any kind of exam question, but you can find this by actually downloading the practice paper, because the ones that I sell that you can find a link to in my shop, if you're wanting to go for these high grades at GCSE, then you've got a good couple of weeks before your physics exams, loads of time to do the papers I've put together, and they all come with mark schemes and work solutions as well. Okay, we now have two circuit diagrams, similar to what we had before, but now we've got lamps rather than resistors, and we've got a battery rather than a single cell. So we've got P, Q, R and S. All of these light bulbs have identical properties. So let's compare the brightness of the following pairs. So in a series circuit, we'd have that potential difference shared between these two components, but we'd have the same current going through both. And that means they've got the same potential difference, they've got the same value of resistance, and they'd have the same current going through them. So P and Q are going to be the same. And actually, what we find is that R and S both have the same potential difference across them. So here we have a parallel circuit, so whatever the voltage is here, we're going to have that same voltage across this lamp and this lamp. And if they have the same resistance, they'd have the same current going through each one. And that means R and S will also have the same brightness. But if we compare P to R, there's a couple of things that kind of stand out. First of all, the potential difference across P is going to be lower because it's shared. So that's going to have half the potential difference of this. And also the current is going to be half of whatever the current would be in one of these, because we've got twice as much resistance in that bit of the loop. So we'd have a lower potential difference and a lower current for P than R. And that means P compared to R, it wouldn't be as bright. Okay, now hopefully that's making sense. I appreciate there's probably nobody in the chat at the moment for GCSE Live, because all of you should be revising biology, but we're going to just keep going. Okay, I suppose this might well be in the background, and maybe at the end we'll have a look at that app and you can have a go at some questions together. Okay, so we need to draw 4 lines connecting the type of interaction with the effect on the electrons in atoms. So this is because atoms interact with electromagnetic radiation. They can either absorb maybe things like infrared, light and ultraviolet, or they can also emit it as electrons go from one energy level to another. I would say with something like this where you've got to draw lines, always do it in pencil first in case you make a mistake. So if an atom absorbs electromagnetic radiation, what's going to happen is that an electron moves into a higher energy level, and that means the electron is going to move further away from the nucleus. Okay, that just means that when the atom emits electromagnetic radiation, the electron moves back to a lower energy level, and it does that as it moves closer to the nucleus. So we have a pattern that looks a bit like this. Okay, so I'm just going to do some lines like this, and that one over there. Okay, I'm just going to put an arrow to show you which is which. Okay, so effectively what we have inside an atom is we have different bands or different energy levels where electrons can exist. So here's my electron over here. And basically, when this electron absorbs some energy, So maybe there's some yellow light being shone on it. The electron might absorb the yellow light and move up to a higher energy level. It's then excited, but as it drops back down to its original state, and it goes back to what we call the ground state, as it drops from the higher energy level, or the outer shell to an inner shell, it then gives out this yellow light in this case, or it could potentially be ultraviolet, other parts of the visible spectrum, or infrared. Okay. The next one, what do we mean by nuclear radiation and ionizing radiation? So this question here is, these are often used interchangeably. Okay, now nuclear radiation, what do we mean by nuclear radiation? So how would we define that? I would say that this is something which is emitted from the nucleus. Now, examples of that could be alpha radiation, beta radiation, or gamma radiation. Okay, we might also have like neutrons given out. Okay, so nuclear radiation, it's something emitted from the nucleus. Excellent, evil. Okay, ionizing radiation. This is not necessarily coming from the nucleus. Okay, so ionizing radiation can ionize atoms. Okay, now examples of ionizing radiation include alpha radiation, beta, and gamma. So these types of nuclear radiation. We can also have ultraviolet, and we can also have things like X-rays. Okay, now of course these two things here are particles, and these things over here are actually electromagnetic waves. Okay, so all of these are ionizing, but only alpha, beta, and gamma are nuclear radiation, which is emitted from the nucleus. Okay, yeah. So there we go. Ionizing radiation can be all these different types of radiation. By the way, thank you everybody for all the love things that keep kind of drifting up in the chat. Yeah, I think you can click on stuff. There's like, I don't quite know what YouTube does with all the stuff. I'm sure it kind of helps send this live stream out to more people. But yeah, you can kind of chat this. You can kind of click the stuff in the side. Make sure you do like the video. I think the video I've had today, I put out a video. I filmed it this morning, put it out at lunchtime, and I think at the moment quite a lot of people are liking the videos. So I think this one's got like 100% likes at the moment, which is quite nice. So yeah, ranked as 1 out of 10 for my most recent videos. But if you want to watch the video, there's a video where I say don't do this, and it's exam advice for 2024. Okay, right, so that one there, that's all good. Right, the next question says, and obviously for those of you who are still here, who aren't doing enough biology and instead doing a little bit more physics, state a type of nuclear radiation that is strongly ionizing. Now the options that we have for this is we have alpha, we've got beta, and we've got gamma. And the one which is strongly ionizing, as Evil says, and Clamor69, is alpha. Okay, alpha is the most strongly ionizing of the nuclear radiations. Okay, the next question, state a type of ionizing radiation that is not classed as nuclear. Okay, so ionizing, not classed as nuclear. You could have ultraviolet, okay, or you could have X-rays. Okay, so gamma is emitted by the nucleus of an unstable radioactive isotope. So the gamma comes from the center of the atom. X-rays are actually formed when we have often electrons decelerating quickly, and the energy in those electrons is then emitted as X-rays. Okay, right. State a type of nuclear radiation with no electric charge. Okay, so which of these has no charge? Well, you should remember that alpha, strongly ionizing, made out of 2 protons and 2 neutrons, has a charge of +2. Beta is a high-speed electron emitted from the nucleus, a charge of -1, and therefore the answer should be gamma. Okay, so gamma, James, Evil, yeah, perfect, good stuff. Right, the next question, super simple. Okay, all of you should know this already because this is going to come up in chemistry. But what we have at the bottom So this one here is thorium is a radioactive element and emits alpha particles to become more stable. Okay, that's irrelevant. You don't need to know any of that stuff to answer the question. And yeah, somebody asked about neutrons. Do you need to know about them? Evil, at GCSE, we tend not to talk about neutrons as a type of thing, radioactive particle or something which is emitted. So although some things do give out neutrons to become more stable, and actually some things also just give out single protons if they're kind of quite light in certain parts of that NZ graph, you don't necessarily need to know about neutrons as a type of nuclear radiation. Okay, right. Calculate the number of protons, neutrons and electrons in the following ion. So we've got something at the bottom where the number at the bottom is the number of protons. The number at the top is the number of neutrons and protons, and that just tells us the overall charge. So Mustang says mass number minus proton number is equal to neutrons. Exactly. So the number of protons is going to be whatever this number is over here, and that's just equal to 90. The number of neutrons is going to be equal to this number here, 232. Take away this number, take away 90, and that's equal to 142. Just checking that in my head. I would say when you're doing your biology papers tomorrow, although there's some stuff where you can do it in your head, it's always worth, when you've got that little bit of time at the end as you're checking through stuff, just to put the numbers into your calculator and double check, even the simple calculations. And then the number of electrons, well, the number of protons is 90. This has got a charge of +4, which means there's going to be 4 more protons than electrons. So we're going to say 90 take away 4 is equal to 86 electrons. Okay, so there's going to be 86 electrons, because basically when you have a normal kind of atom, the number of protons is equal to the number of electrons. So however many protons we have that same number of electrons. But for this ion, what we've done is we've taken away 4 electrons, so it's got a charge of +4. And that means whatever this number is, that kind of keeps going, there's going to be 4 more protons than there are electrons, and that's why we've got 86 electrons. Yes. People didn't see James Stevenson. RTFQ, as I said in my video earlier today, yeah, it's +4 on the screen. And this is why this one's difficult, okay? It's like stuff you know about. It's an ion, not an atom. Yeah, so always read the question. Yeah, there we go. But yeah, James, you're completely correct. In an atom, we'd have an equal number of protons and electrons. In this one, it's a little bit more tricky. Okay, so that was that last GCSE question. What I'll do now is, actually, I probably need your help because I'm not very good at biology, just because I haven't studied it for a long time. So I'm going to use this app over here. Hopefully you can just about, actually, if I do this, okay, that's good, isn't it? Right. Okay, so what we'll do is just 5 minutes of biology revision. To be honest, I don't necessarily know all of the answers. So which of the following correctly describes features of a eukaryotic cell? Is that how you say it? Okay, so is it A, B, C or D? Let me know in the chat what you think it is. So these I cannot say that word, eukaryotic cell, is it divided by mitosis, binary fission, which one is it? D, D, D. Okay, all of you are saying D. Excellent, great work. Plant cells have cell walls which are made from, okay, I do know this one, but put it in the chat, Bramble, everybody else. Cellulose, I'm going to go for that. Cellulose is correct. Very nice. Name cell structure A. So I think before we had B as the cell membrane, I guess C is the cell wall, D is a vacuole. So what is A? What is that thing? Okay, let's see what people are saying in the chat. All of you playing along at home, I'm sure all of you will find this useful if you've got exams tomorrow. Okay, we've got a chloroplast, says Bramble. Bramble, I think you're doing A-level now, aren't you? Is that right? This is just like a bit of revision from a couple of years ago. So chloroplast, says Clamour. Okay, that's good. Which organelle is only found in eukaryotic cells? Oh yeah, there's quite a few A-level people just playing along for fun, although if you're doing A-level biology as well, I think this should be relatively straightforward. Which organelle is only found in eukarya? That word, is it a nucleus? Nucleus. People are saying nucleus. Correct. Nice work, people. Right. Which specialised cell is shown in the diagram? Okay, is that a nerve cell? Is that like your nerves, is it? Eukaryotic. James Stevens says, thank you very much. Nerve cell, neuron, bramble, evil, clamor. Okay, I'm going to go for neuron. Oh, nerves. Oh, what did I say neuron for? Yeah, it's a nerve cell. That's what the answer is for this particular question. What is cell structure D? Okay, I reckon this is a vacuole. The name of cell structure D on this, I reckon it's around the outside of the cell, so I reckon this is going to be the cell membrane. There we go. Okay, this one here, actually, this is a good bit of physics for everybody who's just joined. Right, so we're going to get on to A-level physics quite soon in about 5 minutes. We'll just do maybe 3 or 4 minutes of biology, just for anybody joining this who's got their biology B1 papers tomorrow. Okay, how many orders of magnitude exist between a pin which is 1 millimetre wide and a human hair which is 100 microns wide? So, a micron is 10 to the 6, or 10 to the minus 6, and a millimetre is 10 to the minus 3. But effectively, a micron is 1,000 times smaller than a millimetre, but this is 100 times those thousandths. So the answer would be 1. Do you want me to work that out for you? So basically, the way I see that question there is if you've got, let's do say 1 times 10 to the minus 3, and then you've got the human hair, which is 100 times 10 to the minus 6, because it's a micrometer, and that means 100 times 10 to the minus 6 is the same as 10 times 10 to the minus 5, which is 1 times 10 to the minus 4. So if we compare this number, 1 times 10 to the minus 3, to 1 times 10 to the minus 4, we can see that there's one of them is 10 times bigger than the other, so that's 1 order of magnitude, which is why the answer is 1. Okay. What is 6 nanometers in meters? Again, this is just like physics, isn't it? So, and by the way, this quiz, if I just zoom out a little bit, this quiz is called Bio Quiz, completely free to download. Really useful for anybody who's got their exams tomorrow. Okay, I'm just going to, actually that works quite well when it's zoomed in. So what is 6 nanometers in meters? Well, you'd have 6 times 10 to the minus 9. And so I reckon, looking down this list, it's going to be this one at the bottom. Cool, everybody's got the right answer. This is awesome. Plant sap is found in, is that in the vacuole? Evil says vacuole. I guess it kind of makes sense that this sap is this kind of watery liquid. People are saying A. Correct. Okay, I need to look up how I say this word again. Eukaryotic. Okay, in eukaryotic cells, where does aerobic respiration occur? Does that occur in the mitochondria? So where does the respiration occur? Respiration occurs in the mitochondria. Cool. What is 0.1 millimeters in meters? So I think that you've got 0.1 times 10 to the minus 3, which is 1 times 10 to the minus 4 meters. So I'm going to say it's this one down here. Okay, which of these do bacteria have? A nucleus, a vacuole, ribosomes. Do they have plasmids, vacuole and a cell wall? I guess bacteria wouldn't have a cell wall because that's more like plant. So I reckon the first one, is it? Is it A? Oh. Do bacteria have a cell wall, do they? DNA. Okay, plasmids. No. There you go. Got the right answer. Okay. What part of the microscope is shown by arrow B? So let's just look at that. So B, what is that part of the microscope called? The bit that you look down. The bottom one. No? Oh yes, well that's the last question. Objective lens, eyepiece lens. I reckon it's the eyepiece. You can tell I'm not really a biologist. What is the name of cell structure A? So this is, I guess, most of the cell. Well, it's not the cell membrane around the outside. It's not the vacuole. It's not really a chloroplast. Is it cytoplasm? There we go. The function of ribosomes is to do something. So ribosomes, what do they do? Okay. Right. Proteins. B. Make proteins. Protein synthesis. Okay, everybody here, Sufyan, yeah, make proteins is the correct answer. Okay, now if you want to do more stuff, have a look at BioQuiz. You can find that on the App Store. Free to download, loads of questions, and basically you can just choose your topic and do questions for a couple of hours tonight, and that means you'll know everything that you need to for tomorrow. So for all of you out there who are doing GCSE physics biology paper 1 exams tomorrow, hope it goes really well, and that means you're in a good place. You can do some chemistry next week and then physics the week after. So thank you for everybody who's been on the GCSE part of the stream. We're now going to go on to A-level once we open up a bit of Lego. So again, for those who've been following this kind of journey of Lego discovery, I've just realised I can actually focus my camera a lot better up here. We've got this one, and this one so far, which you can sort of see around us. And am I missing one? 1, 2, 3, 4. No, okay, right. So tonight we'll see what we get. We've got this one here. It's Lego time. If you want to contribute to the Lego fund, then you can donate in the chat if you've got access to your parents' kind of credit card details. And we have this one over here. So who's this? This is like this one over here. So this is our Blacktron figure, one of the enemies of the normal space people. So this is a 5th one. This is quite cool. So let's see what we've got. We've got, again, a super cool little base there. So you can see it's got stars on it, which I think is pretty amazing. And I've never seen a Lego arm like that with like 2 arms in it. So yeah, that's pretty cool. So we've got the Blacktron logo on the front, all printed on the back. We've got the legs. Oh, and actually that leg's a bit weird, isn't it? For some reason, I'm sure there's a good reason for that. They have one of these like mouth things as they're breathing, some kind of like zombie thing, some like air filter there. Okay, that's pretty cool. And also, okay, this is nice. They've got like a Mohican thing, which is awesome. I've never seen a Lego Mohican like that. So that's a pretty cool figure. Okay. Bramble say I should do a tour of my Lego collection one day. I probably should, but there's quite a lot there. Okay, so we've got the figure now, and they've got these guns, but I guess we can have 2 of these kind of probably space lasers, as you'd expect. So there we go. They've got 2 space lasers, and they're holding that. So that is the latest in our collection of Lego minifigures. That goes quite nicely, I think, with the one that we had yesterday. So this one here was my personal favourite because it's like somebody on like an extra vehicular activity for like the kind of spacewalk things. I've replaced the lights with some more like realistic looking lights. And then we've got other people like this kind of space chef that we had yesterday. So some pretty cool bits of Lego there. Okay, and I've just got some blue tack on the back to stop them moving. Okay, right, that is enough with the Lego. We should now, I suppose, probably get on to... yeah, I think Astronaut is my favourite, but the one I really want to go for, and I will get at some point, I'm sure, if people keep donating in the chat or buying practice papers, is the one that I'm really after is this one over here. I think that's my personal favourite because there's like a fancy dress costume where somebody is dressed up as that kind of spacecraft. So we'll see what we get over the coming weeks if I can get some more Lego. Okay, right. Finally, though, some A-level stuff. Right, let's do some proper stuff. So the question here is, again, suitable for anybody out there in Year 12 who's revising at the moment. It's a question about pendulums, but actually a lot of this stuff is stuff that all of you can do, and it is going to be completely applicable to anybody doing AS physics as well. If you're not sure about this, then I do have plenty of other AS level physics stuff, some of the year 12 practicals that I've got in my previous live streams that you can find in my playlist on my YouTube channel, or you can find them at alevelphysicsonline.com/live. Okay, so there's lots out there. Okay, so let's have a look. It says we've got a simple pendulum. It's set up with a 50-gram mass on a thread. Okay, this is kind of one of the standard kind of required practicals, but also it's a lot about simple harmonic motion, and a lot of it is about common sense and actually how to set up some apparatus. I'm going to write in black for this one. I'm going to go for a black pen. How do you take an accurate measurement of L? How could that be taken from this? Okay, so what we want to do is think about how you measure the length of that pendulum. Now, the length of the pendulum is not the length of the string. The length of the pendulum is from the pivot point, which is up here, down to the centre of mass of that thing which is going to be oscillating. And so one way you could do it is you could measure the length of the string using a meter ruler, and then you add on the radius of that thing at the bottom. So what you could do is, just using a ruler isn't quite good enough. What you could say is you could, so it's a 50-gram mass on a thread. If that's spherical or circular, then what you could do is you could use a micrometer to measure the diameter of the mass, and then you can use that to calculate the radius. So that's going to be effectively, I'm going to call that little r is going to be the radius of this thing down here. To measure the length of the string, you could do it when it's hanging up, but something else that you can do is basically unclamp it, and you can put it on the desk, and it's a lot easier to measure something on the desk using a meter ruler than trying to measure something that's kind of vertically. So you could say that the length of the string measured while it is on the desk. Okay, and I'm sure that if you've done this before, you'll realise that it's actually quite difficult to get the ruler to maybe the base of the string here and the base of the string there, because it's often, these things aren't completely flat. So if you imagine what it looks like, you're trying to measure like a piece of string, but it's very hard to get the ruler into where the string meets the mass and where the string meets that thing there. So there are a couple of ways that you can maybe improve the accuracy. It then says that the bob is displaced exactly 30 millimeters to the left and then released. Describe how this distance could be reliably repeated so the pendulum is released from exactly the same point each time. So if you had to do this and you always had to leave it where x is equal to 30 millimeters, how could you do that? So what you might think about is using some kind of marker. So maybe what you might have is you have maybe a block of wood, and you kind of put the block of wood down here like that. Okay, so this is going to be my block of wood. And what you could then do is you could push this across and maybe use something like a set square to make sure that it's actually vertical. And basically you release from this thing here each time. So all you need to do is pull this back. And what you also want to make sure is that the distance to the center of the mass is going to be 30 millimeters, but you might need to add on the radius. So for example, let's imagine the diameter was equal to 10 millimeters. Then we know the radius of that mass would be 5 millimeters. And that means this block of wood, for example, would have to be 35 millimeters away from that kind of central equilibrium position. So again, it's just thinking about this kind of like the logical way of actually doing this in real life. Okay, yeah, right. State the effect on the time period if the pendulum was released to an initial amplitude of 10 millimeters rather than 30. So let's imagine they don't pull it back as far, they only pull it back by 10. What would happen to the time period? Would it get bigger, smaller, or would it stay the same? And again, it's great to see so many people in the chat. Hello Luke, Bramble, Mustang, we've got MAE, James, Big, Bartram, Linkslot, so many people, Abdullah. Hope all of you are doing well. Madhya, stays the same. Yeah, basically it stays the same. And the reason for that is that the amplitude is independent of the time period. If it had a smaller amplitude of oscillation, then it wouldn't be travelling as quickly, but it would still take the same time period to go back and forwards. Okay, oh, here we go. Leela, isochronous oscillator. Again, I'm having real difficulty with my words today after doing some of the biology earlier. So iso just means the same, and chronos is to do with time. So we have an oscillator that the time period is going to be the same. And that's why they were used to keep time on grandfather and grandmother clocks in the olden days. Describe the energy transfers that take place as it oscillates from side to side. So this question here is really going back to GCSE. What we're going to have is there's going to be a transfer of energy between the kinetic store and the gravitational potential energy store. But each time it does that, it might lose a very small amount of energy due to friction to the thermal store of the room. So basically there's going to be this transfer between kinetic and potential energy, and then over time these are both going to lead, and this is probably not the best way to explain it, these are both going to increase the thermal store of that room and the surroundings. Okay, we also have the fact, and this is a really good thing from Luke 817, saying how basically when you've got the maximum kinetic energy, that's when it's going to have the minimum gravitational potential energy at the bottom. That's where it's moving really quickly, and as it moves up to the side, it's going to gain gravitational potential energy, but it's going to have a velocity of 0 at this point, and it's going to have the minimum kinetic energy. Okay, calculate a sensible value for the percentage uncertainty in the time period for one oscillation. So this one is tricky, okay? And this uncertainty question, I reckon all of you might get a different answer, but this is my approach. Now it says the time is recorded as 12.62, okay? And that's going to be the time for 10 oscillations. Now, what do you reckon the absolute uncertainty is going to be for this? So what would be, and I'd like all of you to put this in the chat, it doesn't matter if you get the wrong answer, because you can always just like take that kind of point away, you can just like rescind your point you've just made. What would be the absolute uncertainty in this value for the time period? Okay, now there's not one correct answer, but you've got to imagine that somebody is timing this by hand using a stopwatch. So yeah, 0.01, 2 times 0.01, 0.02, 0.01. Okay, all of you are wrong. You're out by a factor of 10. If you think about human reaction time, and so imagine you've got just like your timer, although I might have my stopwatch here and I can start it and I can stop it, it might give me a time to 2 decimal places, to a hundredth of a second, but I would say that human reaction time isn't 0.01 of a second, okay? And if I was maybe timing something and I was kind of trying to judge when to stop it, I might say that my absolute uncertainty might be plus or minus maybe 0.2 of a second, something like that. Bhajar says like between 0.2 and 0.5 of a second. Okay, so I reckon 0.01 is not the right answer, and this is like the exception, because when we have a timing instrument, although it might give us a very precise reading, the actual kind of human error in that timing is going to be between 0.2 and 0.5 of a second. Does that make sense? So let's go for 0.02 seconds is my absolute uncertainty. Now we know that this thing here, the percentage uncertainty is going to be equal to the absolute uncertainty, which in this case is 0.2 of a second, divided by the total time, which is 12.62. And then obviously we multiply that by 100. So we've got 0.2 divided by 12.62 times 100 is about equal to 1.6%. Okay, now you could give it as 1.6%. You might just say, well, we only really know this roughly to one significant figure. So you could also justifiably give this as about 2%. So what we have is 2% error in the timing. which actually is quite a small percentage uncertainty, but that's because what we do is we time something for 10 oscillations. If instead we only timed it for 1 oscillation, we know that that 0.2, our kind of human error in the timing, would be divided by about 1.26, times that by 100, and that's then equal to about 16%. So by taking the time for 10 oscillations rather than 1, we go from like 16% down to 1.6%. Yeah, so basically 0.2%, so plus or minus 0.2 seconds is due to human error. And that's basically due to human reaction time. Okay, you can't really say human error. Why not? Should I be saying reaction time error? Yeah. Okay. Have I been saying the wrong thing there? Should I not be saying human error? Human reaction error. Okay, yeah. So that's due to the timing error of the person, even though it gives a very precise answer. Because it's like, you know, on your phone, stopwatches, they give you something really precise, but that doesn't mean that you're quick enough to be reacting within 100th of a second. Have to say random error in exam. Do I? Alison jumps revamp. Okay. Okay, random error. Do I need to say that? Okay, let's call this the random error. Okay, let's just keep it as random error for tonight. That's fine. Yeah, okay, so let's just say random error rather than human error. Okay, so we know we can work out that percentage uncertainty. So this question so far, there's nothing here that is unsuitable for somebody in year 12. It's about how to take accurate measurements of a setup. It's about the change in energy. It's about looking at absolute uncertainty. So all of these are fine. Right, we then have this thing here. So the velocity time graph of the pendulum as it undergoes simple harmonic motion is shown below. So this is the velocity time graph. So we've got v on this axis, and we can see how the velocity goes from 0, which is going to be at either end when it's got... the velocity is going to be 0 at each end at the highest point when it's got the maximum gravitational potential energy, and then as that gravitational potential energy is transferred to kinetic energy, the kinetic energy is going to go up, the gravitational potential energy is going to go down, and this just goes up and down with this kind of sinusoidal curve. Okay. Right. Sketch the shape of the corresponding kinetic energy time graph with suitable values. So we need to know some suitable values. Of course, if you want to work out the kinetic energy, we do that using a half mv squared. Okay. Now here, the kinetic energy is going to be equal to half of the mass. And it said, back at the start of the question, we've got a mass of 50 grams. So that's times 50 times 10 to the minus 3, because we're converting our mass into grams, from grams into kilograms. We're going to multiply that by, let's look at the maximum velocity. So the maximum velocity over here is 0.15 meters per second. So that's going to be squared. Okay. Right. Okay, right. So let's go for, by the way, Luke, excellent for finding that. Mustang, yeah, thank you everybody. And Mustang, hope it all goes well for your exams very soon. We've got another clarification from Luke, so thank you for doing that. This is from the BBC. Random errors are made by the person carrying out the measuring and are usually down to timing incorrectly. So let's say that last bit, I should have been saying the timing, the error in the timing is due to random error or reading the instrument incorrectly. Okay, let's just keep it like that. Right. So this is the equation we're going to use. So let's work out the maximum value of kinetic energy we'd have. So you've got 0.5 times 50 times 10 to the minus 3 by 0.15 squared. Oh, I've done that wrong. 0.5 times 50 times 10 to the minus 3 times 0.15 squared is equal to 5.625 times 10 to the minus 4. So that is going to be the maximum value of kinetic energy. And that means we can actually start putting some stuff onto the scales here. And I think, bye Mustang, I think that this is a graph that I haven't seen done that often. So we've got a kinetic energy. It's going to be 0 at the bottom here. we're going to go 2, 4, 6. And this is going to be the kinetic energy times 10 to the minus 4 joules. So we're just going to go 2, 4, 6, and we could go -2, -4, and -6. But to be honest, we never have negative values of energy, so we're just going to ignore that. In actual fact, we're going to ignore the whole bottom part of that graph. So although that was there, you don't actually need to use any of that. Okay, so let's have a look at plotting some data. I'm going to do this, I'll just put some green dots. Now, when this has a velocity of 0, the kinetic energy is going to be 0. When the velocity is 0.15, that's going to be our maximum kinetic energy, which is 5.65. So that's 5.65, something like that. And it's going to be 0 over here. Now, you could do the same for all the different parts along that. But basically what we have is a curve that looks like that. Okay. Now, the reason you cannot have negative kinetic energy, Links Alert, that is a great question, is because what we have over here is a half mv squared. Now, say, for example, at this point over here, our velocity is plus 0.15. Here, the maximum negative velocity is going to be equal to minus 0.15. Now, because the kinetic energy is a half mv squared, whatever the negative value is, we'd have a half times the mass times v squared. But when you square a negative number, it still makes a positive number. So every time you work out the kinetic energy, even if you have a negative velocity, because we're multiplying that negative velocity by negative velocity, we get a positive value for energy. So yeah, not a dumb question at all. So actually, when we look at this part over here, we're going to have 0 here, we're going to have 0 over here, and when it's minus 0.15, we'd have again plus 0.5625. So we'd have a line that looks like this. Okay, and of course that would repeat. Excuse my kind of fairly average sketches here, but again, if it's going to be an A-level exam, they're not looking for perfection, but they're looking to see if you've got the right idea. Okay, so this is the kind of thing that we get. Now, this line here in green is going to be the kinetic energy. Okay, and actually, if we were to plot a graph, which hasn't been asked for in the question, if you wanted to plot a graph that has the potential energy of this thing, then what we find is that, and let's imagine we have a perfect oscillator in a vacuum where it just goes back and forwards and there's no energy losses to the surroundings or no thermal energy gained by the surroundings. What we can say is that the total energy is going to be equal to the energy in the kinetic store plus the energy in the gravitational potential energy store. And that means the total energy, if there's no energy losses, would be the same. So if we looked at the total energy of the system, it would be equal to this black line along here. That would have a constant value. If we wanted to look at the amount of gravitational potential energy, well, effectively, when that's got no kinetic energy, it's going to have maximum gravitational. And when it's got maximum kinetic, it's going to have no gravitational, and vice versa. So I'm just going to put in these points over here. And what we can then do is actually look at the other way, the other kind of graph we could plot on the same axis, which would look a bit like this. Okay, effectively the value from the red line added to the value from the green line would be equal. Oh, that's not so good. It's just a quick sketch. Does that make sense? So basically the line in red is equal to the amount of gravitational potential energy. And that means the green line plus the red line make the black line, because the total energy is just equal to the kinetic and the gravitational added together. How's about that then? So, okay, right, so how about that? That is the last bit of the questions from tonight. These ones came from the 19th of September. You could probably use integration to find the total energy too, but Holly, this is only A-level physics. And in A-level physics, you don't really have to be able to integrate or differentiate. It's just assumed that those things don't exist. It's only when you get to university, where you might be doing physics at uni or engineering, that there's integration and differentiation used all the time. Okay, so I would say you could integrate it, but you don't have to. How do you find the GPE? Basically, the GP is basically the same as the total energy of that system, take away the kinetic energy at that point. Okay, so effectively, if you imagine that this is the total energy in black, if you take away the value of the green line, it's going to give you the value that's on that red line. Okay, right. Would you ever get marks for using calculus instead? Potentially. I think that you've got to remember that the people who are marking your exams tend to be like physics teachers or bitter old twisted physics teachers who don't like teaching kids anymore because you're horrible, and therefore they will understand the physics. But I would say you've got to use the simplest method possible, and the simpler method you use, the more likely you are to not make a mistake and get it correct. Okay, so I reckon that is the end of the stream tonight. Thank you for everybody who's been out there. Thank you for everybody who saw the Lego figure being unveiled. And basically, I'm going to be back next week. Now, I've got a few things where I can't do a live stream every single night. If you want to find out when I'm live again and actually what topics I'm doing, you can head over to alevelphysicsonline.com/live. Just go to my A-Level Physics website. There's all the information there so you know what we're doing each night. And also you can see the plans for the coming weeks, especially as we get nearer to the real paper 1s for year 13, paper 2s and paper 3s. Thank you everybody there who's been in the chat. Hopefully you've learned something, even if you're year 12. And if you haven't already done so, go to alevelphysicsonline.com and you should think about signing up for a premium plan to give you access to all the videos. And also there's things there where you can like download things like the derivation sheets and so on. So I'm going to make that a lot clearer over the coming days. But until next time, which won't be Sunday because I'm away up in North Wales, until then, good night and I will see you all soon. Thank you. Goodbye.